Today we're going to talk about some basic assumptions or axioms for the real numbers. Okay, so there are two operations that you do with real numbers. One is addition and the other is multiplication. There are a lot of other operations that you can do, but these are two basic operations, okay? And these are referred to as binary operations. Okay, this is because each of these take two inputs. Okay, so the binary comes from the fact that each is taking two inputs, and they're operations because they're operating on those inputs. They are doing something to those inputs and then spitting something out as the output. Okay, so the picture to have in mind is the one that I've drawn here. Okay, and you can think of addition as kind of an adding machine where I take two inputs and I output something, and the operation that I do for addition is plus, right? So got A and B as inputs. My output is C, where C is equal to A plus B, right? For multiplication, it's very similar. I have A and B as inputs. Now I have D as my output. The operation I'm doing is this times, and D is equal to A times B, okay? So there's nothing new here. It's just a different way of thinking about addition and multiplication as adding and multiplying machines that take two inputs and spit out an output. Okay, there's a little bit of terminology convention that the inputs for addition are referred to as terms, and the output is referred to as the sum. For multiplication, the inputs are referred to as factors, and the output is referred to as the product. Okay? Now, the rules that we use when adding or multiplying real numbers are going to be based on a few basic statements. So I'm going to write this down so that you have it in your notes. Rules So our rules for addition and multiplication are based on a few basic statements. Okay, these basic statements are also called axioms or postulates. Okay, and I'm now going to go through a handful of axioms. So when I was a student, I think my algebra book largely referred to these assumptions as axioms, and then my geometry book largely referred to them as postulates. They mean the same thing though. All right, so the first axiom that we're going to talk about, the first two axioms, are the axioms of closure. And the reason that we concern ourselves with the axioms of closure is that we ask the question, if I have two inputs to my adding machine, is my output also, so if I have two inputs to my adding machine that are real numbers, is my output also going to be a real number? So is that output a real number? If I have two real numbers as input to my multiplying machine, is that output going to be a real number? Well, let's consider an example. Okay, let's say that a equals 5, b equals 7. These are both clearly real numbers. When I add these together, I get 12, which is also a real number. When I multiply these together, I get 35. That's also a real number. So maybe now my intuition tells me that, yeah, if I take two real numbers and I add them or I multiply them, I'm going to get a real number. And that's actually true. For all real numbers a and b, a plus b is going to be real, and a times b is going to be real. So that's our first two axioms. One thing that I want to go over with regard to closure is that you can do this over, or you can ask whether any set is closed under any operation, right? So when we talk about closure, we're really talking about, I've got some operator, and the two operators that we've looked at so far are addition and multiplication. But this could have been subtraction, it could have been division, it could have been some other star operator where maybe star is defined as, a star b is a to the b plus b to the a, right? So we've got some operator and we've got some set that we're considering. So far we looked at the real numbers. This could have been the set of integers, could have been the set of natural numbers, anything. Okay, so again, when we talk about closure, is this operator closed under this set? In other words, if I take two elements from this set and I apply this operator to those two numbers and I get my output, is that output going to be in the set of numbers that I started with, or that I, had pulled my two inputs from? Okay, let's take a look at an example of a set that is not closed under addition. And it's going to be a really simple set. It's just going to be 1, 2, 3. That's going to be my set. And my operator is going to be addition. Is this closed? That's the question that I'm asking. Is my set 1, 2, 3 closed under my addition operation? Well, in order to show that it's not closed, I just have to find a counterexample where two inputs from this set give me a number that's not in that set. Okay, so this is pretty easy. I could take 2 and 3 as my two inputs. That's going to give me 5. And 5 is not an element of 1, 2, 3. So therefore, 1, 2, 3 as a set is not closed under addition as the operator. Now, I could have defined plus to be something different from the standard plus that we're used to. I could have said, hey, I'm going to define plus as a plus b is always equal to a. I could have just defined it that way. In which case, my set would be closed under this definition of the addition operator. Now, why I would call this plus, I don't know. Probably I would have called this star, so a star b is always a. All right, that's a little bit of an aside though. Okay, the next set of axioms that we're going to talk about are the commutative axioms. And these are pretty simple. They just say that for all real numbers, a and b, a plus b equals b plus a, and a times b equals b times a. It doesn't matter what order I write these two inputs in. When I apply the operator to the two inputs, the operator addition or multiplication to the two inputs, oops, I totally wrote this wrong, I get the same answer, okay? We kind of already knew that, right? Like 5 plus 2, which is 7, is the same as 2 plus 5, right? Or 2 times 5, 10, is the same as 5 times 2. Okay, the commutative axioms are just formalizing that. Okay, the next two axioms that we'll talk about are the associative axioms. And these say for all real numbers a, b, and c, a plus b plus c equals a plus the quantity b plus c. And a times b quantity times c is the same as a times the quantity b times c. Okay? So together, the commutative and associative axioms are permitting you to add or multiply numbers in any order and in any group of two. Okay. The last set of axioms that we're going to talk about are the axioms of equality. So again, this is for all real a, b, and c. We have the reflexive axiom, which is saying that a equals a. So just a equals itself. That makes sense. The symmetric axiom, which is saying that if a equals b, then b also equals a, right? If two things are equal, it doesn't really matter which one is on the left side or the right side of the equality sign. They're both equal. Finally, we have the transitive axiom, which says if a equals b and b equals c, then a equals c. Right? So we know that a is b, we know that b is c. Since a is b and b is c, then a must also be c. Okay, that's it for today.